So Nilanjana had to leave, and we appointed Viv as the second chairman, but she had a dental emergence. So I, as an organizer, I have to take. So instead of a nice lady, you have an ugly man, but I think you will be recompensating an excellent talk. And our next speaker is Professor Michal Solomiak, and he will speak about squeezing. What's that? He will tell you squeezing a region of a particle shape.
Mm-hmm. Thank you for the invitation to be here, and I will speak about the eigenvalues of the Dirichlet Laplacian in a narrow strip, and this is a joint work with Leonid Friedlander. Actually, it is rather difficult for me to give this talk after the so brilliant preceding talk. And one of these difficulties comes from the fact that I prepared two introductions, but almost everything from my first introduction already was said. Nevertheless, I will explain something. This is an old problem. Study what happens happens with the eigenvalues of the Laplacian if in the domain which shrinks to some curve or to some graph, in general to some set of smaller dimension. And there are many papers about this situation, and it is well understood that there is a big difference between the cases of Dirichlet Laplacian and Neumann Laplacian, and in particular for the Neumann Laplacian, it is well known that the eigenvalues, that the spectrum tends to the eigenvalues tends to the eigenvalues of the Laplacian on the graph, and this means from the on the first sight it looks strange, since say if everything happens on the plane, then our original problem is two-dimensional and our limiting problem is one-dimensional, so there is much more eigenvalues for the two-dimensional problem, but the rest eigenvalues simply escape to infinity. And for the Dirichlet Laplacian, the situation is different. First of all the eigenvalues escape to infinity, so we have to normalize the problem, to subtract some universal term, and then not always it is a bad term. Usually, the limiting behavior of the spectrum after this subtraction is determined not by the Laplacian on the original, on this limiting object, but by some other operator which has to be specified. I believe that the most famous problem of this type is concerns eigenvalues in narrow tubes, where Pavel Exner and Sheba, and later it was the paper by Duclos and Exner. They found that the limiting operator is Schrödinger operator with the so-called curvature-induced potential. And there are many other results of this type. And so this is more or less introduction number 1. Introduction number 2, I am afraid that again, after the lecture of my predecessors, it is not quite true what I was going to say now. But nevertheless, my belief, at least was before this lecture, that in most cases, this convergence of eigenvalues cannot be some independent fact, some independent effect. My belief was that usually it should be only a consequence of a sort of resolvent convergence in norm. It is difficult, it is not so easy to describe this belief in general terms, simply because for these shrinking structures we are dealing with different spaces, and so one has to somehow interpret what is in each case this resolvent convergence in norm. And this I will try to explain on the very simple example which we did analyze together with, as I already said, with Lenny Friedlander. This is simply a model case. So the situation is extremely simple. Namely, our graph is just a segment, a linear segment. But the profile of the domain is determined by a curve, by a graph. This is a function h of x. So the one difference between this case and usually considered case is that here the width of the domain is variable. Usually one considers the constant h of x, at least far from vertices. And here we have functions. I take this maximum point as the origin, and so we have this function h which satisfies the following properties. First of all, it has only one, so suppose this is minus EB and this is and the function, I repeated, it has only maximum at the point, at the 0 point, and it is smooth, and its Taylor decomposition at 0 is like this. M and C are positive numbers, and we consider the family of domains omega epsilon, which are just x is from I, and y is between is positive and is below h of x. Sorry? Power, in the usual case, it is of course 2. This Morse case. But for any, the result will be written for any m.
Odd one, right?
Even.
Who is even?
If m is 3.
No, sorry.
Oh, okay.
This is better. This is better. Now, what are the results? I already said that, according to my belief, the convergence of eigenvalues should be a consequence of some results about formulated in terms of the resolvent convergence in norm. But before coming to this deeper type of formulations, I formulate the result in terms of eigenvalues. This is theorem 1. And it says, let us consider this operator. On the whole axis. So this is an harmonic oscillator. And let us denote by mu j its eigenvalues, and let us denote by lambda j of epsilon eigenvalues of the Laplacian. I consider the positive Laplacian. Then we have the following under these assumptions. We have the following asymptotics of lambda j. This term is clear. It appears because the whole spectrum escapes to infinity. But there is also the second term of asymptotics, namely mu j over epsilon to power 2 alpha, and alpha is 1 over m plus 1.
2m plus 1 or m plus 1?
No, it is. This is 2 alpha. No, this is correct. This is correct. This is the result in terms of spectrum. Now I will try to explain how to consider it, how to introduce the sort of resolvent convergence in this problem.
Q should be C probably. You have parameter C, Z, and Q in another problem.
Sorry?
Q. What is
Q,
Q?
Q should be related to the previous problem.
Q is C.
Q is C, yeah. The parameter before x to m, Q,
The frequency
on
of
the
the
top.
Well, no,
What is
this-
Q? Q, what is it?
How is Q defined in terms of this? It's related to C.
no. I did not. Sorry. Sorry, I did not specify Q, indeed. Indeed. To pi squared C m cube. Now everything is written here. Something else is missed?
Yes.
No.
A and B plus no. A and B plus no. Actually the steps which are necessary for treating this problem in the terms of resolvent convergence are more or less standard. So what I will do now is well known, and I believe that many people could do this. First of all, we have to define the one. We have defined subspace in L2 of omega epsilon, which is responsible for this asymptotics, and it should be the subspace which is a natural way is a metric to L2 on the interval, and it is absolutely clear what should be this subspace. Namely, we consider the subspace which I denote by L epsilon, and which consists of function which are defined by some given function chi on the axis, and which is now normalizing and this standard function which appears in the evident way. If we take this, then of course this function has the same norm as the function chi in L2 on the interval. And what happens, and now we calculate the quadratic form. The quadratic form, our quadratic form is of course the Dirichlet integral. And It is straightforward. It is a straightforward calculation, so rather lengthy. One has to be careful. And it leads us to the formula that and class term which does not involve this parameter. And what is this function v? Actually, it is not very important, but it is constant, namely this one. So this is a positive term. And now it is clear that the main contribution to the spectrum is given by this term, and not by this term in the whole, but rather by the point, by the value of by the maximal value of h. So we subtract this term in which we replace h by m, and we get a quadratic form which I denote by q epsilon. This is quadratic form, integral. It is enough to work on real valued functions, so I no more will write the sign of absolute value. So we have this. This is nothing but minus this m squared, p squared, m squared, epsilon squared, this is this term. So W is pi squared over epsilon squared, and here 1 of h squared minus m squared, and plus v of x. So we have this quadratic form, and it is clear what is the corresponding operator. This is the operator given. I will write it here. This operator is q epsilon and with the Dirichlet boundary condition on Dirichlet on the boundary. Good. And here is the first result. I will compare the result. I will compare the resolvent of the original operator, original Laplacian here, and this operator on the interval, but of course complemented resolvent. It's better if I write down the theorem. There are numbers R naught and epsilon naught such that for any epsilon between 0 and epsilon naught, the following estimate takes place. This is my Laplacian. We subtract this term. This is one operator, and we subtract the inverse to Q epsilon, orthogonal sum with 0. 0 is, of course, on the subspace which is orthogonal to this space L epsilon. And it turns out that for small epsilon, this does not exceed. This does not exceed R0, R naught. So here is the estimate. This shows that this difference decays quite fast. So this is the first reduction, which actually reduces the problem to dimension 1. But of course it is not enough, since we have to find out, we have to consider what happens, how to reduce the case of this finite interval. We are still here, we still live on this finite interval, but our limiting operator acts on the hollow axis, so we need one more step. What is this step? This is, of course, this is scaling. We consider the dilation, this dilation, epsilon to power alpha, and we get this interval J epsilon and then this interval I epsilon, and G epsilon is just the unitary mapping of L2 on the original interval to onto the new L2, which is given by this dilation. And this is the operator which we get after this unitary mapping, after we multiply it by here it is. These operators already act on L2 on the wider interval, and the next result says that these operators which we complement by zero operator outside this wide interval. And the difference between this term and this goes to zero as epsilon goes to zero. These two theorems, 2 and 3, they immediately imply the results which was written here. This is just arithmetics. And in this case, I treat this combination of these two theorems as interpretation, as a proper interpretation of resolvent convergence in norm for our case. And now I will not explain it, is just arithmetics, but I will give now another interpretation of theorem 3, which is less convenient for proof, but I believe that it is more convenient for it is more transparent. Namely, let us consider the following family of operators in L2 on the axis. We have operator H, but along with H, let us define this Q, epsilon to minus squared, x to power 2m. So these are self-adjoint operator, only the coefficient is a bit different. And now if we make scaling, then we see that the operators that these operators form an isospectral family. So it is an isospectral family of self-adjoint operators. And an equivalent formulation of this fact is this. if we take the family of our original operators, not original, no, but already acting on the one-dimensional interval, and we take this as a spectral family, then this goes to 0. So the picture here is like this. Our operator don't approach an individual self-adjoint operator. They approach a family, and is a spectral family. Here, so this is the situation, but because this family is isospectral, then it gives the desired result for eigenvalues. This approximation of an isospectral family, it is a fact which was recently studied by Yoram Last and Barry Simon in more complicated situation of essential spectrum. But here, the same ideology applies to the discrete spectrum. Fine. Now, I would like to say several words about proof. It is not difficult, but I will outline the most important steps. On the first step, we find that the norms of these inverse operators decay also for some decay sufficiently fast. This is not difficult, and the way to obtain this estimate is to look at the quadratic form and again to do scaling. So this is simple. More difficult step is to prove this theorem 2, to prove this result, and for this reason, to achieve this goal, we compare the quadratic form of two operators. One operator is actually the operator which we need, and another operator is its diagonal part. What does it mean, diagonal part? We have the decomposition. One subspace is our L epsilon, which is described here, and another it is its orthogonal decomposition, orthogonal complement. Unfortunately, this this decomposition does not reduce the operator A epsilon. So the main problem is to estimate its non-diagonal part. Fortunately, this non-diagonal part is small. It is small not only in L2 norm, which would be not enough, of course. But it is also small in the Sobolev norm of H1. To see this, one needs some estimates, and it is necessary to be careful. But this is the result. And after this non-diagonal part is estimated, then the remaining part of proof is more or less standard. It is the most convenient way is to use some version of Hilbert resolvent formula, but in terms of quadratic forms. It is not difficult. And so this estimate leads to theorem 2. Now theorem 3 is its proof is based on the following result, which is not difficult, and I will be glad to get some reference provided that this exists. I did not see this in literature and could not find it, but I repeated that I cannot consider it as an independent result. Here we have the following picture. We see that our operator Q epsilon, it acts on the finite interval. But the final operator H acts on the whole of axis. When after this scaling, we we extend our interval, but nevertheless it is still an interval, not the axis. So here is the lemma which helps to manage everything here. Suppose that V is non-negative potential on the axis such that growing into V at infinity. And suppose we have that we have a family of expanding family of intervals. Say In. They expand, and the union is the whole of R. And then we compare the operator, let's say Z. This is just Schrödinger with this potential, and then the operators Zn are defined by the same differential expression, and the Dirichlet condition to be more precise, this means that each operator Zn is the direct sum of the interior Dirichlet operator and exterior Dirichlet operator. So if we have these objects, then we have this norm convergence of the resolvents. I repeated that the result is not difficult, and I even try to explain the proof. Say weak convergence in this case is actually evident. Weak convergence or even strong convergence is well known. Now, the operators Gn and the operator G satisfy this inequality in the sense of quadratic forms. Just since the quadratic form coincide, but the quadratic form of Gn has narrower domain than that of G. This implies that for inverse operators, we have the inverse inequality. That this is just the opposite. The n are greater than z. But then the n to pi, then we have this inequality as a result. And now there is a theorem which is there is a theorem in Barrier-Simon's book about trace ideal methods, that if we have such family of operators which converge strongly or even weakly, and besides all the operators have the common majorand, then actually, and this common majorand is a compact operator, then we have convergence in norm. And here just this works. I am sure that there are many other proofs. And this result, or some of its modification, is used in order to prove a theorem, which one simply looks at this potential W epsilon, and then after this dilation, we come to a sequence of potentials which behaves exactly like this. These potentials, they approximate this function, which is written q x to power 2m, and satisfy also some necessary inequality in order to get this theorem, and so this is the way to get the result. Now let me make some concluding remarks. What can be said about this problem itself? First of all, it is certainly simpler than the problem with the neighborhood of constant width, just because we have to take care about some neighborhood of this point of maximum. Say nothing depends on the original interval. If we consider such interval, then nothing changes. And this, of course, has some important applications. First, what happens if we consider this problem not not on an interval, but suppose that we are dealing with, say, with junction. With junction and around each. Yes, of course, nothing changed, nothing important changed here if we take two-sided neighborhood of this. And so suppose that we have such sort of junction, and we have its own function h around each edge, and I'm interested in the behavior of Laplacian in what we get here. I don't describe the problem in detail, since it is only about its flavor. Then, if we suppose, if we assume that for each function h, its maximum is attained not in the vertex but another point, then in limit we have just the orthogonal sum of these operators. This is remark number one, or maybe not number one. Then, what happens if we have the similar problem on the whole axis? So again, we have a function which with only one maximum, and of course one needs to suppose some nice behavior of h at infinity. What happens then? Practically nothing will change, but of course some details in the proof will change. In particular, then this theorem, this result is not sufficient to handle this case, because our potentials will not tend to infinity, but there is some another version of this theorem from Simon's book, and so everything goes in the same way. And then the next question, possible question is, what happens if this function h has its maximum at the boundary point? Then, of course, this number to m is not necessarily even, but nothing important happens. We simply have some operator on the semi-axis as the limiting object instead of the operator on the whole axis. And otherwise the results survive. What I don't know is what happens if if our function h is periodic. Since it is clear the character of result is more or less clear, since the Floquet decomposition can be carried through and give some result, but I don't know how to identify, how to formulate it in terms of resolvent convergence. I don't know yet what is the corresponding limiting operator. Maybe, yes, that is, and that is all. Thank you.
Questions, please? Yeah, Eve.
Yes. Do you know something if the function is piecewise linear? I mean, if the domain is a polygon.
Something like this, yes?
Like this, yes.
It is certainly, we did not look at this, but we kept it in mind. It is clear that here the result is of the same type, but only the,
But your reduction,
it is like the case of the maximal point at the end of the operator. So we will get the operator with this sort of
I'm not
potential.
sure, because you know, in your reduction, your V of x, there is some h prime of x square, so maybe there is some delta potential here, I'm not sure.
No,
Because in this reduction, you get, when you compute the quadratic form,
Yes.
you have integral of t prime square
yes,
plus v of x and plus this p square over epsilon square h square plus v of x. But v of x now, there is a derivative which
Is
is
different.
which gives some kind of delta potential because the derivative of.
yes, but
You will do it on the right and you will do it on the left. And then,
But then there is some green condition and like a delta potential.
I agree.
There's something to-
I agree with you that the computation is necessary here, but I believe that this is correct formulation. I think this is the picture.
Similar question maybe if the asymptotic is different to the left and right, you have say linear and quadratic. What can happen? Will the
What is the
so
picture?
if you take a linear here and quadratic here, so
then you will get it.
As soon as you
I think, no, it is even clear. Since different powers of m, let me write it here in this way, so m might be, or, and your question consists in the fact that in the left neighborhood we have one sort of behavior and then another. This eigenvalues, you see that we have this alpha which depends on m. So here we have two values of alpha and one is Wien.
so will it be the half oscillator and
No, only one. One half, the
Yeah.
smallest half will disappear. Smallest interval alpha.
David was first.
What happens if your function h vanishes on the boundary?
H what?
Vanishes
zero.
on the boundary, zero on the boundary.
Maybe I did not. Yeah.
If h vanishes on the, if h is zero,
It's zero on the boundary. For example,
Like this, yes?
yes.
I think
if it vanishes by power.
that I think that nothing awful, but strangely enough, we didn't look at this case. We will look. Say something like this.
yeah, but
It is.
as long as you have the maximum, it's important what's happening around the maximum. yeah?
Yes, but so that is why I think that nothing serious happens, but I'm not sure. I'm not sure since here we have a free Laplacian, and it survives here. So it's useful to look at this case. So it certainly cannot be difficult.
Will something change if you have a tube instead of a one-dimensional? Or
It is
several-
possible. Yes, it is. It's possible. We looked at this simplest case, but of course, tube is possible, and also many-dimensional analog is possible when we have a domain and say two-dimensional domain and three-dimensional domain omega epsilon. I don't foresee any serious complications.
Yeah.
You said that when you have a boundary, maximum on the boundary, then 2m can be odd, right?
Yes,
Because
this
then
I
when-
said.
Then the model probably have something that looks like our equation, right?
No. Since only half line, then our limiting object is an operator on the half line.
Expressible in terms of hard terms.
So no effects like this.
Okay, any more questions? If not, let's thank Professor. Now we have just a technical.